What I want to do is continue our discussion. First, I'm going to go through the material we've done before, lay down the plan again. It's very good to do so because this is quite a complicated setup, this whole Newtonian mechanics. And after a while, everything starts turning in your head. And even after years of doing this, it's very difficult to escape the illusion that this thing is totally circular, you know? And it isn't. It is actually working, but it takes a while, all right, to really understand it. But let's first reiterate why we're here. We're here to define something that we're going to call the economic motive force. This is the same role as the motive force, or we don't really use this terminology anymore. We say the driving force or something like that in Newtonian mechanics, and the electromotive force in electrodynamics. All right? So it's an agent or a cause for the motion. All right? And by motion here, we're going to mean the flow of goods and services and all that kind of stuff. All right? This is something that's lacking in economics because economics is all about equilibrium. And what we're going to do here is talk about dynamics, how things are changing. And that doesn't preclude equilibrium. You know, once you know how things are changing, you can sort out when things are not changing, and then you've got equilibrium. All right? Now, this motive force has got all kinds of names. It's a want, or a desire, or an incentive. We're going to find all kinds of ideas for it. All right? But what it is not a price. Okay? That's what I want to say here. Now, economists do not look at a force. They always look at price. In order to determine whether equilibrium is the case or not, they will say that the prices are equal. We will not do this. Somehow the forces have to balance, all right? Not the prices are equal. So something else is going to happen, all right? Now, there have been previous attempts also in the engineering literature to do this kind of stuff. And invariably, all of them assume that force is analogous to price, all right? This is the one thing where we depart from all these things, all right? So it's not going to be a price, it's going to be the time derivative of the price, okay? This is the big change, all right? And everything is going to fall out of it. So in a sense, F is speed up, that's Newton's law, and the rest is details, okay? There's just a whole lot of details, okay? So this is what I want to put down at the beginning. We're going to look at this force. It's a totally new way of doing it, all right? Nobody's done this before. It's a big challenge to set the whole thing up, all right, in this way. That's what we're going to do, all right? So what I'm going to do is follow the publication. We have a link on it in the descriptions of the, we're making this nice playlist, and there's a link on it, but you can find it yourself in archive. And there are several chapters, and here are the chapters. And we'll go through it 2, 3, 4, 5, 6, 7. All right? And it's based on Newton's Principia, published in 1686. And a lot of the, you see what happened, this guy, Adam Smith, he is considered to be the father of economics. And he was writing in 16, what is this? I can't even read this. MDCC 1776 here, right? Yeah. So that's already 100 years after Newton, but their thinking was very different than modern economists. They thought in terms of forces because they were so influenced by Newton's seminal work. You know, Newton really hit the world, or at least the Western world, like a bomb, and later on the whole world. All right, when they saw what kind of ships you could make with it and cannons you can build with it, and everybody will buy this. All right. So these, and even Marshall here in the 19th century, so this is 1895, you see him referring to the forces of demand and the forces of supply, and he starts describing economic equilibrium in terms of some balance of forces, but he doesn't purely, hand wavy. He never has a definition of force. All right. Huh? Then later economists, what happens with economics, it kind of went on until the Second World War, and then a lot of mathematicians moved in. And they kind of moved away from this more physical way of thinking, more intuitive way of thinking, and then economics became, at least the theoretical part, very mathematically oriented, kind of theorem proof kind of thing. All right. For the engineer, this is way more attractive. Okay. All right. So this is what we're going to do. Today, I want to finish the definition section and then talk about the laws. All right. And then almost done in understanding the structure. Okay. Now here are the various things we're going to do. We're going to try to finish this table. But before I do, I kind of want to say something about how all this hangs together. So all of Newtonian mechanics can actually be said in like two equations, maybe four. Okay. So the first two are definitions, and the other two are assumptions. So the first is that you define something you call the velocity as the time derivative of the position. All right, I'm using Q for position because it corresponds to quantity in economics, and also it's used for the canonical variables in the Lagrangian thing. This is the definition. Nobody tells you that velocity should be that time derivative, right? Okay, you got to define something. All right. We are going to use this definition also, and we're going to define the quantity demanded or the flow of goods as the change in time of some account balance or some imaginary stock that we have. All right, this is not what economists do. So this is the first thing you do. It's just a definition. Then the second thing, it's called a law, but really it's not a law. It's also a definition. That is that we define a force to be the time rate of change of momentum. There's another definition. So one of the weird things of mechanical engineering is that you start statics and then strength of materials and then dynamics and all of this stuff. And you just are told that you have a force and they have to balance. So nobody has ever given you a definition of a force. You just get used to it. All right? So nobody really knows what it is. It's just a thing. And you can take a partial derivative of potential energy, you will get a force. And you can also take a time derivative of momentum, you also get a force. But why all this has to be equal, nobody knows, right? You get used to it after a while, okay? So this is one way, and that's the modern way to kind of think of Newton's laws, is that really it's not a law, the second law, it's a definition of force, all right? So we have two definitions here. Okay, that's the definition we will use. Instead of P momentum, we'll use price, and we let the force be the rate at which you're changing your price. You're adjusting your price, right? So the intuition is clear. If you want something, so you have a want, right? You're going to increase the price, right? All right, just bidding it up or asking it down. Okay. Now, of course, you cannot have a theory with just a bunch of definitions. All right. So there's a couple of assumptions that are in there. And the first thing is that this V here is a function of momentum. All right? Now the function you have, you all know, is 1 over m times P, and that's okay. Right? That's an assumption. That's not a definition. All right? Because you can make other assumptions here. Like for light, you can't write this down because it has no mass, and for quantum part, it doesn't work. Relativistically, it doesn't work, right? This is an assumption. All right, it's a basic assumption. Okay? We're going to get that too. And that one, weirdly enough, Newton has placed in the definitions, whereas this definition is in the laws. All right? It's all a little bit. But I don't fault the man because, it's sometimes, sometimes you can see definitions as just clever ways to define stuff so that the law just looks easy, right? So how would you know to define it if you don't know what you're going to assume as a law? So it's always a little bit, tricky like that, okay? Now there's a second one. That is where does our F come from? Okay, you see? Now you can make all kinds of assumptions. You can assume it's a function of Q, like that it's k times q, then you're on a string. Huh? But you can also make an assumption that it depends on the velocity, that's v times the velocity, or you can assume that it's constant, like gravity, right? Huh? M times g, right? You do the weird stuff here, okay? And these are all force laws. Huh? And that's what we're gonna deal with in a separate chapter, okay? But I just want you to just appreciate this simple setup, right? So here, these two things, okay, and then these two things, all right? Huh? And this would be here or something else. Huh? Okay? Huh? All right? Huh? This one's a little bit special. You can make this function of something else, but it will position against, but it's not very. In mechanical engineering, it's not. Okay. This one we are way liberal. We have forces coming out of every loop, crabby, and crack, and but we don't have momentum and velocities coming out of everything. All right? Huh? So we'll keep that in mind. Okay? Now, what is Newtonian mechanics? What is it saying? All right? These are two differential equations, right? So these are two differential equations. All right? And these two things, what they do is they couple these two differential equations, because you see this guy here depends on that guy over there, and that guy here depends on that guy over there. Okay? So you see they're coupled. Huh? So what Newtonian mechanics is saying, that the mathematical structure of coupled differential equations is what describes nature. Okay? That's the basic law. All right? That's a non-trivial statement. Who says that it should be two second order, a couple second order, first order equation? Why not second or fifth or, why? Okay? Why are these constants one? Well, actually, it's some other choice. Huh? Okay? So that's the real impact of this whole thing. And what is then economic engineering? That is that this same structure of two coupled differential equations accurately describes a dynamic theory of the man. Okay? That's what we're going to try to do. All right? Once you see that, then the thing stops being circular. What is the force? Now, the force is defined like this, but you can measure it in various other ways. These are sometimes called constitutive equations. Okay? All right. Huh? Okay. What's the velocity? Well, you can look at the momentum and find out, but really, this is the definition, right? Huh? Okay. But these are the coupling. So these constitutive equations give you the coupling. All right. Huh? That is a Newtonian idea. It's very simple, and it takes a long time before you see the simplicity. All right. Huh? Okay. So our job is then to argue ourselves through that we know all of this, that this is right. I see you nodding because you've done all these courses and you're going like, okay. But now we want to say, how can we fit this all, economics in the same framework? All right? Now, you have to appreciate that it's not clear at all that this will work. I mean, you can't just assume that anything can be described by a set of first-order equations. So it's sort of a miracle that it works. There's also a miracle in electrodynamics, does it? Because this is the electric current, right? This is the charge, and this is the voltage, this is the flux, the magnetic flux, right? So what Maxwell saw was that the flux, the magnetic flux, and the charge, they influence each other, and that creates electrodynamics. And you see this same coupling, right? You also see that with first order second differential equations, you get these A matrices, the state space, you get oscillations, because if you work it out, you get second order equations, you get everything. All right? You can do your Laplace transform, okay? Now, we have a bunch of variables here, right? F, P, Q, V, right? So here they all are. And then we throw in one more, the derivative of the velocity. That's for purposes of calculating. Because when we take this derivative, we're going to end up with, and then we take that to be n times v, then we're going to end up with a second Now that's the only reason for it. Okay. Now in the definition section, we're going to do this one, do this one, do this one, and we're going to do this one, and do this one. We also will do this one, but this one goes to the walls. All right. Okay. And unfortunately, we're going to do this one. We'll do it in the definitions. Huh? But the only reason it makes sense is because of the laws again that we'll do later. So here we kind of have to believe this is okay, and then in the laws we'll justify it. All right? Huh? Okay, that's the first law that justifies this choice. The second law is this definition, and the third law tells you that this definition is a good one because it tells you momentum is conserved, and if it's not conserved, what the heck are you doing taking a derivative? In time, your result is conserved either. There's any one but something weird can happen. All right? Huh? So really, you see, these laws are just there to tell you that this is a little bit unclear why, what is the definition of what's a law. But Newton did it this way, we know it this way, we call it this way, so that's how we're going to do it. All right? Huh? Clear? This is an important point. It takes a while to appreciate that pure simplicity. And it's one of the beautiful things of mechanical engineering. You're forced to do something. You can live your whole life as a mechanical engineer and have no idea why this is working. All right? And what the real assumptions are. Somebody asks you what force is, you tell them, I don't know. Right? It's just there. It's just, nobody can answer the question. What's the time derivative of momentum? Oh, I don't know that. Okay? All right. So the first thing we did was introduce demand itself as inertia, right? And then we can also look at these bigger bodies. You see, the problem with Newton's law is that you talk about this idealized particle, and Newton realized that. And he's talking about a big Earth, and then you just kind of have this center of mass and it behaves as if it is. You're far away enough, the thing looks like a point anyway, right? So I introduced that. Okay, and then I went ahead and here I did this definition, right? Okay, so the flow of goods is equal to the rate of change of the balance in some accounts. Okay, and so vectors. Okay. And then you can also define this guy. It's a little trickier how to do that, but we won't discuss that. That's acceleration. That's sometimes called the extension of the demand. All right. And the thing to see here is that the space in which this all occurs, that's in Newtonian mechanics is physical space, that's what we call commodity space, right? So each of these axes is a certain commodity, so these are, say, apples, these are bananas, all right? And then the value here is the actual balance in the account, right? The account is the type, and the value is the balance, okay? And the rate at which you're going is a vector, and that's your activity, all right? So you kind of, there's a subtle difference between the dimension, the value of a variable in that dimension, so keep them all, good to keep them all separate. And then the coordinate system is called the chart of accounts. This is some terminology accountants use, right? So they think of this big chart and chart about, ledger. All right. So that's our space. So our space can have any type of dimensions. And don't immediately think it's Euclidean, so you really don't know what the distance is, for instance. You wouldn't know what this angle is unless you add some structure. We'll do that. All right? All right, you can do the same thing for the center of mass. Okay. Now we're going to define price. Now, the way this is done in Newtonian mechanics, it's defined. They call this the definition of momentum. All right? Huh? Now, that's a little bit unfortunate because it really isn't. But this is just what it's called. All right? So it's not a definition, it's more of a constitutive law. And there was a guy who came up with it, that was Descartes. And he didn't use vectors here, but that was Huygens who fixed it and used vectors. Right? So you should read this as a vector equation. Okay? But it's not a definition, it's just called a definition. All right? Huh? Now, one of the things economists do, and here's a picture of Marshall's, is that they will plot the demand line sloping down and supply line sloping up. All right, so this is the diminishing marginal utility, and these are the increasing marginal cost they'll have. All right, now obviously this Peters and V line is not sloping down, it's sloping up, and secondly, it's going through zero. So what's happening? All right, so the first thing that's happening while this is sloping down is because this y here, that is p, is always a positive number. Okay, so somehow they made the same mistake that Descartes made, that they only want to look at the absolute value of this thing. Okay, so they don't look at negative values of this x, which is their velocity. Okay. So what we will do is calibrate these lines so that they will always go through zero, right? So this thing will go through zero. We also assume that they're straight. Later on we can drop that. Okay. But in Newtonian mechanics, you assume the mass is just constant most of the time. You can change it by throwing some stuff on it, but that is the time process, okay? And what we'll also do is associate, like in this case, you would associate positive flows with supply, and then negative flows will be with demand, so this thing will flip, right? Huh? So this thing will flip, and it will look like that. And then you have to get it to go through zero, and then you can make a line like that. Okay? So the thing to realize is negative values for the flow of goods are implying negative values for the price. Now it's up to you to decide whether your negative flows are from the supplier or from the demander. Normally what you do is you have a system, and then the flow goes to the right, and then you assume that that's the positive, but you can think of that for, right? You just have to make a choice, and then the other one is on the other direction. Okay? All right? Then there's another issue is how you go the heck through zero, and we'll solve this all in later, but the answer is going to be, it's actually right here, and it's not solved later. Let's do it right here. Now, well, the answer will come later, still. But what we do is, and we'll talk about that, but the point is here is that when you say this object has a velocity, you can't just say that. You have to say it's a velocity with respect to something else. So this pen has a velocity with respect to me in my hand, that is zero, even if I move it, right? But it has a higher velocity with respect to you, who's sitting still all of a sudden. So the momentum of the pen for you is a bigger number than for the observer sitting here. Okay, so you can shift this thing up and down, and you need to assume something about this business, and that's in Newton's first law, where you do that velocity is relative, and we'll get to that. Okay. There's a big other thing that we're going to do differently. So for now, just assume that we can do that. Huh? So this whole figure of Marshall's, I cannot put here. So I have positive prices and negative. Sometimes it's convenient to call that a bid, right? And this S, and here I put the buyer on the positive, right? Here the seller is in positive. What does it matter, right? Huh? So he's buying, he's selling. Huh? He's acquiring, he's disposing of it, so it's even better. Huh? Okay? And he's asking, he's bidding. He's got the asking price and he's got the bid price. Okay? It's just some different terminology. So that's what I refer to as a unified demand schedule, because we unify the consumer and the producer, or demand and supply. All right. Economists think of these characters as different, right? So you have all these consumers and they own the demand, and they have producers and they own the supply. But we're going to take a slightly more symmetrical point of view that anybody can demand or supply, and actually it's relative. Okay? All right? So you see there's quite a bit of work to do to kind of get rid of the ideas of price and quantity demand that you've learned in Econ 101, right? You got to kind of, keep some, but shed enough, right? Huh? Okay. Huh? So negative price doesn't mean negative like you would think. It means, no, it's the other side of the transaction, okay? That's how we can get momentum to get conserved, the price to be, value to be conserved, quantity. Otherwise, it won't be conserved, you know? Huh? And the whole thing won't work. Okay. All right. Then Newton just introduces this idea of a force. Boom. And the reason he does this is because everybody was already using this. All right. So he just went ahead and says, well, you know, I'm going to make some definitions. I'm going to call this that, and I'm going to call this that. Not sure where the word force comes from. It's probably from the Latin, probably from the fasces. Huh? You know, that symbol that the Romans had for the power, huh? You know, it goes to these, and there was that axe coming out of it, huh? I don't know. You gotta look it up. We say kracht, huh? They're just a Germanic word. But it's a word that's been around. And what we're going to do to fix our intuition is to say, well, we can call it a want, or a desire, or a motive, or this is another good one, a price action, or some feeling of scarcity, right? Huh? But that also is some kind of, it generates some kind of desire. So if you're free of any desires, you kind of relax and you don't feel any. The idea is as soon as you feel you want something, right? Want something, there's a force, economic force acting on you. You're going to do something. Okay? That's the call to action. First, you got to want something. If you don't want anything, you're not going to do anything economically. All right? Huh? Then, in order, if you want something, you got to incentivize somebody else to do that. Okay? So those are the antonyms, like the reaction forces. It's an incentive or an effort I have to make. You could also call it a price reaction. Huh? Okay? Convenience instead of scarcity, friction that you have to overcome, right? Economic frictions. Okay? So, of course, you have to really think of this wanting, huh? In Dutch, behoefte, right? You gotta have this desire, all right? And you can use it as a noun or a verb. I desire this, I want this, it is a want. You can even make an adjective out of it. You can call it desirability, or it's a level. You can call it all kinds of stuff. And it comes in all kinds of things. Right? Now, the motive is already built in. Right? I think that's actually one of the nicer ones. Why didn't Newton call it the motive force? Because he felt the force went in. That was his idea. The force goes in the mass, and it accumulates there as momentum. That's what F is P dot means. P dot is a flux, and F is a flow of momentum in that mass, okay? Right? And that motivates that thing to move, as it were, right? Okay? And the way we want to do it, that want goes in you, your want kind of accumulates, all your desires accumulate to motivate you to start buying stuff or selling stuff or things like that. Okay? All right? So that's the idea of the force, right? So don't think of it as a price, that won't work. If it is a price, then force is a price, then you gotta have something else, a big P, that you take the derivative of to get momentum. It doesn't exist, okay? It's not gonna work. Your whole thing will fall apart. All your couple differential equations, everything. All right? Now, Newton goes ahead and makes a couple of definitions that we want to use. The first one is this thing, the rate of change of price, okay? Momentum. What is our rate of change of price? He calls that the inertial force. And I will call this the force of demand, basically because that's what Marshall and everybody talks about. So when they talk about demand line, they talk about demand, you have to adjust your price, right? And if the price goes higher, then you demand, whatever, more or less, whatever, okay? So the rate at which you change your price must be the force of demand, right? Because demand is what is sitting in here, right? T is intensity. Okay? It's inertia. Actually, demand was inertia, so the inertia force must be the demand force. All right? It's easier. Okay? We just define demand as inertia. So, all right? And then you have the motive force. This is what Newton called the motive force. That's what goes in there. That's what we call the economic motive force, right? All right? Okay? We're going to end up with more from other forces, but those are the two basic ones. Because with those, you can write down this, right? Okay. And then there's another thing. I have it in the paper a little later, but I decided to put it here. Otherwise, is if you look at the impulse, all right? The Stone's very nice. It's a little bit confusing because what we call impulse, it induces momentum, and our state is their impulse. It's all right. So this is some about dp, right? That is really an inducement. So in English, there's a difference between a want and an inducement. You see, a want is something that hasn't been realized yet. An inducement has been realized. So if you have a want, if you want something and you want that over a period of time, you are induced, to raise your price. Okay? All right? So the right translation for the impulse is an inducement. There's a subtle difference. Okay? This whole business is pretty subtle, right? So language is very rich because we deal with money all the time and we deal with economic things all the time. So we have a lot of terms. And as it is often, is that these have a rather delicate meaning that we're not even aware of. That we really have to unravel and say, wow, this is really this really it's just that, right? Okay. Here's a quote by Marshall. I thoroughly sink in because it really tells you that they were. So he talks about the force of an economic motive. Okay? This is what he writes, literally. So it's like an economic motive force, right? It concerns itself chiefly. We're going to just say always, right? With those desires, so you see there you go. He uses aspirations and other affections of human nature. So this is also a good thing, affections of human nature. So he says it's a personal thing, right? This price here is your price. It's that masses, that body's momentum, and not some other body, right? It's not the market price or some agreeable price, no, it's your price. It's what you personally attach to it at that moment in time. All right? So that's why he says, how I read affections of human nature. The outward manifestations of which appear as incentives to action. Okay? Here you see another using the word, And action, that's just to change the quality of the event, right? So this will be the action, the acceleration, right? Okay? So if you read these kind of things, it's a little bit bombastic language because that's how they like to write in the 19th century. They thought that was cool, right? And they didn't have WhatsApp yet where it takes forever to type this. And you get spell checked, half of the stuff. But as you can see, the idea is basically there. It's just not formulated. It's just not formulated mathematically. But it strikes me when I read Marshall, it's a pretty big book. There's a lot of war, but if you read closely, you see it's lying there. Just an extra step, just to write an FSP on. That's not made. But intuition is there, except nobody ever did anything with it. Right? And then they went ahead and started proving equilibrium for very complicated arrow de Bruce securities and other ones. All right. So I find these things interesting. Okay. All right. So this was a biggie, but you see, this is okay. We have it now lying there. We have some intuition, and then we'll sort out exactly how the details go. All right. All right. Now, if I go back to this, now we have done basically everything except. Where was the big table of mine? Oh, here it is. You see what I have? Here I have two different, what I call analogs. These are called analogs. Okay. And we use in engineering two different ones. There's the mobility one, which is used in Newtonian mechanics, and it's also called the admittance analog by electrical engineers. And this is the impedance analog. Okay. The source of this is that the Newtonian mechanics just works differently, conjugate to the way electrodynamics works. Okay. So if you have a spring, right, and you put a force on it, what we imagine is that force going through the spring. Okay. And if we look at the deflection, we consider this as sort of a level change, a level, height, or say it, if I put it up like that, and you see the height, somehow the level changes. All right. So the force goes through, right, and the velocity is a level change. It's over. We call it sometimes a cross variable. All right. And in electrodynamics, it's exactly the other way around. All right, so here's the capacitor, and the force is over, okay, it's the voltage drop, not the height drop, right? And the current goes through. All right? So it's exactly the other way around, okay? And there's a bit of a switching. If you have a system, an electrical system, and it's in parallel, you'll have to be, mechanical equivalent will be in series and vice versa. There's all kinds of little things that come out of this confusion, all right? So we talk about strong forces and a large amount of momentum, right? But we talk about voltage drops, right? And high levels of magnetic flux, okay? All right? So there's a switch. And we just do it. All mechanical engineers keep themselves to this one, the mobility analog as a picture. That's also Newton's picture, right? Because you see the force as a flow, right? Okay, so it has to go through. Okay. And all electrical engineers use this picture here. In economics, you can use both. And it all depends what the problem is, what the application is. So we just have to come to grips that there are these two ways of talking about it. And often when you do your research, if you draw an electrical circuit, you just have to use this analogy. And if you draw these mechanical equivalent circuits, you have to use this one in order for it to make sense. All right? Okay? Now what I want to do is go through that in some detail. And the reason I'm doing that now, and in the paper it's in the appendix and I talked over it, but basically because I didn't want to bog it down, but here I'm going to do it because it really gives you some exercise using these terms and thinking about them before we launch in these laws, all right? So I'm going to do it a little bit different here, all right? So the first thing I want to do is go through this mobility analog, and that's the one that pertains to mechanics. So I drew a picture here that's a little bit nicer than the one I was just sketching. The mass spring in the damper. So that's the demand, that's the economic friction, that's a storage law. We'll find out about that later. Now what happens here is that this thing will have a P dot going this way, change of momentum, and there's some spring force looking like this, and there's a friction force going through there. All right? Huh? And the thing is, the amount you have of storage, the position is this Q, and then there's this change in level, dq, which is represented by the velocity. Okay? Huh? That's the picture. This is how you would draw it. So you see forces a momentum flow through. So there's an amount of momentum here flowing through. So there is a level at which the thing is that can increase or decrease. Okay? Now how does that translate? That means that, look, a balance. So this Q is not really a quantity, a stock quantity. It's more of a balance feeling, because a balance can be high or low, right? If I turn this thing upside down, you could see it was high or low, right? Huh? A balance is a level. You don't have a balanced quantity. So the correct mobility analog for position is a balance in the account, okay? Not a quantity in storage. Understand? Huh? You see the difference? That's the natural way to do it. And then the velocity will be the flow. It will not be a flow, but it will be a level at which the level of the quantity demanded. All right? Huh? So the demand is high or the demand is low doesn't mean that the flow is big or small. Now it means that this level is rather large. All right? Huh? Okay. Huh? Level's not large. Level is high. Okay. All right. Huh? You see that? Huh? So when we say demand for these goods is high, we're really talking this, right? Because high and low are levels. Huh? Okay. Now this has to go through. Now price doesn't really flow, does it? That's kind of open. So what you really want to do instead of prices, instead of that, use personal value. It's just the value that I ascribe to it, right? Me personally. Rather that you can say that it's like price, but this value can flow out of you. That's like reducing the price, right? And to someone else. Okay? So this one, that's just a flow of this value. So by wanting something, you're increasing or decreasing the amount of value you assign to it. Okay? Huh? Okay? So what we do in economics, sometimes we will call this price, but it's always in this context, in this balance, but it's a little bit uncomfortable, you know? This is kind of the precise way to look at it, okay? All right? So this is the one that fits the best with Newtonian mechanics, okay? And this is the one that fits the best with electrodynamics and also with these pneumatic things. And this is, I put this picture out here just because you see here, notice the goods that are, it's not, the demand is not at a high or low level, they have these goods flowing, right? So they have all this stuff flowing here, and then other stuff flowing, and then draw these little arrows. So it looks more like, you know, a current going through here, right? And here I drew a hydraulic picture, and here there's just this flow going through, okay? So rather than I don't know why I put quantity demanded here. You could put that. Yeah, I know why I put it, because now it's a quantity, but you can also call it, this is really a flow quantity demanded, right? Economists talk about the quantity demanded, right? But that's kind of confusing because it's really a flow. We sometimes call this a volume, actually, but it's really the volumetric flow rate. Huh? Okay? So you have the level of demand, and demand is high or low, but you can have a flow of the quantity demanded, which can be big or small. All right, huh? So slightly different terminology and a different picture. All right, price is indeed a level, but you say the price is high. We don't say the price is big, right? Huh? So it's really the level variable. Huh? And instead of the desire, we would say the desirability for a level. Huh? You know? So you would have a desirability drop. You know, you can't have a desire drop, right? Huh? So desirability drop. You can say wanability, except it's not a word. Huh? All right. Huh? This is acquisitions. That's the volume. It's like a large amount of acquisitions you did, and you have the balance level will be high, and you have a big amount of acquisitions or something. Okay. So just be aware of this. Okay. That a lot of people mix and match it, and we will do so. But there are these two analogies, and this is okay. Huh? You can read about it more in the paper. This is the kind of what people have in mind a lot, you know, when they think of economics. It's kind of thing, right? So they see these goods flowing. And you have all these things, these storages, and there's some storage and there's some friction. They actually draw these things like a system dynamics. They draw this, you know, they draw this kind of stuff. You know which one that's always missing? This element here, right? You never see it. The paddle wheel, right? Because the paddle wheel, that's the analog to the inductor, right? That's the thing that keeps that flow going, no matter what, right? If you leave that out, this thing can stop any moment. All right. So here's the price. It's going to be in this paddle wheel. So there's a lot of these flow graphs. There's somebody who in the 70s made a whole computer, you know, I think the 60s even, of economics. And all these capacitors and resistors. No paddle wheels. It's like having a circuit without an inductor. I mean, once you're an electron, you have no dynamics. You just have all the capacitors are going to discharge over the resistor, and then it's done. Huh? You know, huh? Okay. Huh? All right. Yeah. Okay. Just it's in the paper, but you see there's a little bit of a terminological thing. All right. Huh? Depends on what type of economist. Agent-based guys do this. Demand, the theory of demand uses levels for demand. The demand is high, whatever. Huh? There's a big flow of goods. Huh? All right. So I think we're done now with that, with these definitions, and I want to proceed with the laws. All right. So there are three laws, as you know. There's 1, 2, and 3. This is how you remember them. The first one is free motion. Second one is the law of motion. And the other one is usually called action equal reaction. And we're going to give those an economic meaning. And this is what I feel is the closest. The first one will be freedom of want. Huh? So want is a force, and freedom of want will be to be force free. Right? Huh? That's really what this is, free. Free motion means force free. Right? It's a little bit tricky what Newton does, because there's his first law where he says when there are no forces acting, but he hasn't defined a force yet. Right? So you see, it's all a little bit, but the poor guy, I mean, there's a lot to do. All right. Now, this law of motion, that's the biggie. And we'll call it the law of demand, but it really is a sort of a dynamic version of the law of demand, right? The law of demand is just this thing goes down, right, or up, huh? And you can just see this as big, huh? What I really want to say is that F to speed up is the law of demand, but there are different ways that the law of demand is described, and I just decided for this because it's catchy. And this action's reaction is going to be that the forces of demand should always balance the forces of supply. All right? Huh? So, and I just try to put them in these catchy things. All right. Otherwise, you get these complicated things. All right. So let's go. So I put a nice picture here. And this picture is by an artist that used to be very popular, still is in the United States. And it's called Freedom from What? And this picture was made, it was published everywhere. And it was one of the 4 freedoms. And it was very popular. They were formulated by Franklin Delano Roosevelt, who was the US president at the time, FDR. And he postulated this was all after the Second World War, and that must be before the Second World War, because afterwards he was dead. He died during the Second World War. So it must be before. But people were really trying to define a new kind of world order. You know, they'd seen that the First World War didn't work out, and then they had to motivate themselves to fight another world war. And then they had these ideals, and one of them was what they said was the freedom from what. Okay? Now I find that these guys eating an enormous amount of food, so they're, but whatever. So this is what FDR said, which translated into world terms means economic understandings which will secure to every nation healthy peacetime life for its own. So this is the idea, right? So in worldly terms, so we talk about nations, it's just what we call a healthy peacetime, nothing more, nothing less, just your basic needs being fulfilled or something like that, right? So you could think it just allows you to consume, standard rates. You don't have to first have 100 and overeat, you know. You have so many apples and so many pounds of hagelslag, etc. All right? So you're not feeling any want, they are okay. These guys are celebrating. That's exactly what you don't really mean. You just mean you can just keep cruising, right? But not pretty end because these things are iconic. All right, so how do we translate that? Okay, so the idea is that, so Newton's idea is that a body of rest goes at a constant speed, right? Now this is a brilliant idea, because before they didn't think so. There's Kepler thought that these planets, they can't move by themselves, there must be angels pushing them or something, right? Everybody thinks that you need a force to have motion, and that's not such a stupid thing to say, because on Earth, everything is like that. I mean, this thing doesn't keep moving forever. Neither does this thing, neither do you, right? Neither does anybody, right? So here's a dude who's formulating a law, basic law, which cannot be verified on Earth, okay? Because all of it are exceptions, okay? So you have to appreciate the guts of this guy, all right? Because the first theorem is obviously false, right? So before that, they thought the law was false because Aristotle had a law that everything fell by its natural rate, right? So you had all these elements like fire that went up, right? And then water kind of went down, right? And Earth really went down, And then they had all these things, you know. And you would think that because you're going to let something fall and it's going to go after a little while by constant rate due to the, the compensatory effect of friction that goes down. You would think everything has some kind of natural rate of falling down, right? Except fire that tends to go up. So these are all reasonable things to do because they correspond to measurements, okay? Now, you can also say, and that I think was Galileo, we have a little bit of a problem there, because he said, well, the natural thing for planets to do is to go in circles. So they were finding a natural thing for things to do. So they go these circles, but they did. They went in an ellipse, all right? Now, why is that so natural? Well, because it's the most beautiful shape, and blah, blah, So you sit there, but never do you find anything that goes in a straight line at constant speed. Right? So no single observation does that. All right? And yet, there's somebody comes with a law and says that's the best law of nature, and everything does that. And all what you see are exceptions to this law because there's always a force present. Because something that goes at a constant rate passes by you in the universe and you see it only a few times and you're never going to, if you do econometric models, you're never going to see it. Right? Okay? Now, what we need to do is stand on the shoulder of this giant and just posit the same thing for economics. So what is a constant velocity? That's a constant level of demand or a constant flow of goods, depending on the mobility analog or the impedance analog, right? And I'm just going to say that any agent in rest consumes at a constant, acquires at a constant rate. Okay? That's it. All right? That's my assumption. And Newton also said that's the condition of being force-free. Okay? So he's already made a little bit of a definition of a force as a change in momentum, you see? He's halfway there. So I'm just going to say, without looking back, that's the condition to be free of wants. Okay? And that's this freedom of wants. Okay? So I'm going to say that if you are consuming, or if you are producing, or if you're buying, or if you're selling, or whatever you're doing at a constant rate, then you're going to be in this Newtonian rest situation where where you're free of wants. Okay? I think that's correct. If we, as a society here in the Netherlands, consume so many barrels of oil a day, and we keep doing that, we are free of want and desires. We don't desire more, we don't desire less, we get exactly, as many barrels as we need. Okay? The mistake to make is that you need 0 barrels of oil, in order to be at rest. Okay? It's not the case. Okay? You don't even know what rest is, you don't even know what a zero position is, you don't even know what a zero velocity is, you don't know any of that. Right? Okay? Okay? So this is a basic assumption. So you got to go along with that. I think it's okay, but you got to put that in your head. All right? Now, once you put that in your head, you're in trouble. And everybody was in trouble on this issue until Galileo kind of saw the point. Okay? So if you say, all right, how do I measure this velocity I'm going at? How am I going to measure that? Now, let me ask you this. How do you measure that? So you put yourself in a room, you close all the windows, and you're going at some velocity. How would you measure what velocity you're going at? Yeah, you can't, right? But do you know that you're going at a constant velocity? You do. Because if you didn't, you wouldn't be able to walk to the bathroom without going like this. And if you would take this pen and drop it, it will go like, I don't know where it will go, right? So every time, without looking at anything else, just inside yourself, that you're going at this constant velocity, but you have no idea what the amount, the rate is. Okay? Right? That's called the theorem of relativity. All right? Right? Okay? So another person who's going at a different velocity, if you have 2 of them, you can measure what the relative speed of one is to the other. Okay? That you can do. Because you can go in here and look at that guy and then see how far you're going apart or getting close. All right? Huh? Now what we normally do is we take one huge wall or earth or something, it's called an inertial reference frame, and we assume that has velocity 0. When we say we have velocity Vd, that means it's with respect to this thing. So I have some kind of beeper, zoomer, speed gun. He's standing on this, and he's looking at how fast you're going. But without that, you can't. Right? So the only thing you can do, really, is measure differences in velocity. Okay? This is called the... it's not a theorem. What is it called? Of relativity. It's the postulate of relativity. All right? Postulate of relativity. And it's made famous by Einstein. It was formulated by Galileo. It was made famous by Einstein because he used that, he assumed this postulate would remain valid and then worked out what would happen if the speed of light was a constant, you see. Because that's supposed to keep the light as a constant. And many people say, well, that's trivial. But it's not so trivial because suppose it's going like this, and then I'm sitting on another light ray, right? And I'm looking at this light, you are sitting on that light ray. But then I still see you going at the speed of light because it's a constant, right? For all observers. How is that possible? Right? Okay, so people say, I don't think the word, it's ridiculous. And so the postulate of relativity must be wrong. And it turns out that that's the wrong assumption. You got to assume that it's right and then work out that everything else is wrong. Okay? Position is wrong, time is wrong, all the stuff that you thought you know. Then you have the theory of relativity. So it was called the theory of relativity because this thing was taken as the, the God-given thing. Okay? Huh? All right? Huh? Doesn't mean that things are relative, all the things that people say that it does. All right? So this is the postulate of relativity. Okay? We have to do this, once we've assumed through this, first of all, we have to do the same with economics. Okay? So if you're just sitting there chopping away, breathing air, you have no idea how much air you're breathing, right? You can only measure, if you need more air or something, then you, let's say it's available, then you start feeling something. You don't know what this other person is breathing, whether he's panting heavily or stop breathing altogether. That also happens. Okay? But what you can do is look at that other person and then compare, right? Okay? And you look at that difference in consumption rates, or demand rates, or flow rates. Okay? And that difference is either positive or is negative, right? When it's positive, what do I have here? So I have the supplier and the demander. So here I have the demander and here I have the supplier. So this thing is positive because this one is bigger than that. So here I have something that we would call the excess demand. So that's my demand. Well, I'm demanding an excess over this supplier. Okay? And that's what makes this person the demander and that person supplier, not because he's absolutely positive, because if I take this thing, there's other, he is still demanding from them. But he can be supplying to this demander here. All right? Okay. All right?
So if you're an agent in a room with no other agents, you don't know how much you want something.
No. You can't measure that. You can call that zero. And that's what we typically do, right? Right? So there's just a point at which you calibrate yourself. And then that's why the demand line goes to zero, right? Because you assume that this guy could have assumed that his velocity is zero and this is zero, right? So he's in a reference frame connected to that. So he is assuming he's demanding from out just zero. Then you have to say this guy must be negative, and this guy must be even more negative. So these are both suppliers. This one's supplying a crap load, and this one a little bit less, right? Understand? But from this person's perspective, these are all demanders, right? Okay. So you see, that's what makes this whole thing work, is that this theory of relativity means that I can flip, that I can go through zero, because I know what zero is. I have to take some kind of reference frame, call that zero, and then I can get my unified event schedule to go through zero like this. See? Remember this thing I had here? What is this zero out here? If I don't know what velocity is, the level, I need to choose some zero. So I take one, I have to assume one thing, and that's what we call an inertial reference frame. Okay? Now Newton spent a lot of time looking for inertial reference frame, right? So he got really frustrated because he couldn't find one, because the Earth is obviously not one. That's what everybody uses. Then the sun is also not one, right? And then when he finally postulated that it was the average of all the stars in the universe, right? So some center of mass. And even that doesn't work because how far does he have to integrate? And you just gotta give up. And then there's a modern interpretation, slightly different. It says what the first law does is postulate the existence of such a reference frame. And you don't have to have it in actuality. You just have to assume there's one there and just draw it. Yeah, boom, there it is. Okay? So for economics, it means that there's the existence of some benchmark, okay, from which you can measure all demand. All right? That's the assumption. That's the basic thing this law is saying, that exists. Although you may never observe it. It doesn't matter. All right? And with that, so this is this possibility of the existence of it, so that we can calculate velocities relative to that. We can calculate demand relative to that. We can divide people into suppliers and demanding. The demand is depending whether they're more or less than this benchmark. All right? Okay? It's a bit of a subtle business, okay? But this is the way you resolve it. So as soon as you make I see a lot of student models that go wrong on this because they take, okay, here's the quantity demand is that, there the flow is that, and there is this, and they're all measured in different frames, you know? So you're mixing, matching all these velocities in different, again, nonsense, all right? So when you make a bond graph or something else, you've got to take some inertial reference frame and then, okay? So before you start modeling, just make your assumptions on what are what's your reference velocity. In impedance analog, it's a little bit unfortunate that they have these two. It works a little bit different. You don't have a reference velocity, but you have a reference force. Later we'll talk about how you. So the ground, that's a reference voltage, right? Doesn't have a velocity. There's not a current. There's not a reference current. It's a reference voltage level. So it's slightly different. So this wall here is replaced by earth. There's also a ground, but this is the mechanical ground, which has zero velocity, and the electrical ground has a zero voltage. All right, by assumption. Okay. It works a little bit different. A little bit confusing, all of this. But they just made the wrong choice. They should have they shouldn't have taken charge to be analogous to position. They should have taken it analogous to momentum, and then everything would have worked out. But that wasn't done, and it's okay. We can work with both systems. So if you do these electrical things like in Kuhn, you'll see that the reference is going to be a desirability level. So you have to have things at the zero desirability level. Like Beerity has that, right? Okay. And when you make these mechanical kind of things, you have a zero demand level. All right? Clear? So you can't really talk about the demand that's out there. It's always the excess over something else. And when you do, there's an assumption that you've chosen a reference level of demand. Okay? All right?
And we take this excess demand is what we would call supply if you apply the third law.
Yeah, if it's a negative, then it will be called the excess demand negative, it will be supply. Right?
Yeah, if you incorporate the third law, because then you have actions reaction. Because right now you just have an action.
Yeah, well, let's get to that when we get there, because I think it's a little bit confusing. Sorry, you're on the right track, but let's just do this step by step. All right, you just got to get this in your head, because many errors are made if you don't understand this. Okay. So in order to get this all to work, we need to assume Galilean relativity for the theory of demand. All right, now economists don't do that, so their prices are all over the place. All right, so they always get these things to intersect, but we don't really need. It makes no sense. These things have to go to zero because you need to, take your reference. When the velocity is zero with respect to the frame, you can't have momentum. So when you're not demanding anything with respect to your benchmark, or the market, say this is a market, you know, that means your price is zero, okay? You're on the same price level as the market, you know, your price is basically, so you're not willing to bid over, you're not willing to bid for it, okay? Huh? All right, huh? So there are some subtleties here, which you're going to get wrong, and then you've got to like lasso yourself back again because it's so confusing, you know, now it can be really confusing. Okay. So I like the reason that I like that you're thinking ahead, but then I'm going like, oh my God, there's so many little things. It's so easy to slip. There's so many banana peels, you know. You face plant yourself really quickly, you know, this business. Huh? Really quickly. All right, let's keep going. Now here comes the biggie with the law of motion as a dynamic law of motion. All right. Okay. Now, we've already talked about it quite a few times, so it shouldn't come as a surprise. Normally, what's stated is this, okay? So what you define, of course, is the time rate of change of momentum. So what we're going to say, your desires, they are the time rate of change of your price. Now, this is actually not what Newton said. Newton actually said this. He didn't really look at these derivatives. When you read what he writes this, all right? But this is a perfectly other way to say it, is that you look at this inducement here, and that is a small price increase, right? Okay? Now, this is the mobility analog, so this gives it as a flow, and this gives it as a change in level, all right? Price level, and this is a flow of value picture. That's the only difference. We always use this thing in engineering, right? But these electrical engineers, they would like to. They write the voltage DT is d lambda or something. They sit and they did a little bit different. Huh? Huh? Now, there's a slightly different feel to it. So this one, Newton, he invented this notation for the derivative. Did you know that? Huh? This is dp dt. And this notation didn't exist yet. There was Leibniz who came up with it later. And at the time Newton was writing, that also tells you that this guy is like amazing. There was no calculus. So they didn't know how to take the derivative. So while he was writing his Principia, he had to invent calculus on the fly. And then he had his notation. So he called this a fluxion, right, in Latin. When I was studying here a long time ago, they still call it flux in Dutch also. Huh? And fluxy P would be, the flux of P would be P dot. We say now in English P dot, I believe, right? Huh? Does anybody say fluxy P or so? Huh? I remember the old guy, when I was really young, going, fluxy P, fluxy this. Huh? But a fluxion, flux comes from the Latin word of flow, right? Huh? Flux and flow was
double fluxion?
Yeah. Double fluxie, huh? Huh? And he also had, you know, it was kind of, it was nice for one or two, but not so nice to have four, right? And so, and the other thing is, how did he do an integral? You know how he did an integral? So he does the integral of P. Huh? How do you write that? Huh? This is what he did. He made a box. Huh? Well, it is kind of a box, right? An integral. Huh? You know. Huh? Okay. So it's what you accumulate in your box, and this is what flows. Huh? So you see, Newton really saw forces of flow of momentum, right? This is the picture he has, flowing in there. It's a nice picture, you know, like, even if you look at a static situation, like, for instance, you have this door and there are supports in here, And then there's all this momentum that's being poured in by gravity. Like gravity throws momentum in all the beams and the roof, and it has to flow down. So it flows down, in these flux lines, right? And it has to make a really sharp corner over here. That's what will break, right? Because you're forcing this. So when they build these cathedrals, they have these flying buttresses, these Gothic cathedrals go way up in the sky. And the reason they were doing it, because they were able to get the flow of momentum from the roof going down smoothly, right? Instead of building like the Romanesque cathedrals where they were like this, and they had these big walls. But the bigger you made the walls, the more momentum would flow in there. And then the roof would be on top of it, and the thing would just, super thick, and it would work. All right. It's a very nice picture to see force as the flow of something. It's just flowing through the system. Okay. And that's kind of a Newtonian picture. So that's what you see here, right? So you have the thing, and it's filling this thing up with momentum, and whatever. Okay. Then this picture is slightly different. And this is, you can think of this as a marginal price. So there's a whole thing in economics called marginalism, where you look at the marginal this and the marginal that. It's a recent thing from the neoclassics, and they saw, okay, the thing that's not important is price itself, but marginal prices, marginal changes. So there's very much in line with what we're doing here, right? So looking at marginal changes. So yeah, maybe that's all I'm going to say about that. So this is when you're bidding up, you just bring the thing up, and this may go on. I have a nice picture here, and I want to think through what this means. So what this means is that if this is price, then a flow of momentum, this must be F, because that's speed up, right? Okay? All right? Now, how do you get that? There's basically three ways to get that, and they all have, economists have figures next to it. So this, if you take this one, okay, this is your definition, this is your unified demand schedule, you plug it in there. What are you going to get? Well, you get F is dmv dt, right? So that is m times v dot plus v times m dot. All right? This is what we call A. A lot of people forget this term, right? And think that Newton said F is and say that's not true. He said this. This is a consequence of what he says. All right? So there's also a force if you change the mass, right? We know that, right? You have a car that's moving, and you throw something on it, and it's going to move less fast, right? There's a force pushing it back. All right? So let's look at these separately. First, this one. Now here's P is F times V. That's this line here, this red line. All right? This is F. And this is A, right? Okay. So what this law is saying F is M times A is that you are here at this price level, at this level of demand, right? And what does that force do? Okay. It jacks up your price level, but at the same time, it brings your demand level up. All right? Okay?
Did we feed off?
Feed dot.
And it's Q dot.
Thank you. Thank you. Exactly. Of course, right? And this is V, and I'm changing V. So this is also called an extension of the demand. So I'm demanding more at a particular rate. I'm starting to demand more. And then because of that, I'm jacking up my price. at this rate. Okay? Huh? All right. If I keep the price elasticity constant, then all this is saying is that I'm moving along this demand curve. That's what FSM is saying. Is that clear? Huh? In fact, economists call this a movement along the demand curve. If you look it up, this is what they call a movement along the demand curve. So the F is M times A portion is what an economist would call a movement along the demand curve. All right? You see that? Huh? You look a little worried. Huh?
I think it's strange that they still use the force.
What?
Still be strange to use the force if they already knew this, right?
They just don't call it a force. They just call it a movement along the demand curve.
Oh,
But they don't. See, what they don't see is that if you set it up with a unified demand schedule, then that portion is exactly the FSM times A portion of Newton's law, right? You see, what we get is all kinds of stuff that they do, but you find it as components of this theory. You understand? Huh? Can we get the guys back? Huh?
I think they're back up.
Sure. Huh? Oh, we just didn't see you. Huh? So I like your remark. It's like kind of crazy because the fit is so good. You go like, well, wait a minute, right? Huh? Okay. Huh? Then what is this thing saying? If you're writing everything times A, well, you know, well, this is your wants or your desires. This is your needs. All the time. It's that, you know, the needs is what happens here. This is your need. So you need more, you know, more apples per day, right? And in order to get that, you gotta want it, right? And jack up your price. Okay? Huh? Okay? Huh? I find there's something simple and beautiful about that, you know? Like I looked it up on the internet and all kinds of other places. You have philosophers, they're always talking about the difference between desires and needs. Huh? You know, and it always comes down to something like that. Needs are things that are really concerned with the good themselves, and desires are this thing that's more abstract that is motivating you to do this, right? Huh? And this is really a beautiful way to do it. I prefer to write A as epsilon times F, you know, because this is the cause and this is the effect. Okay? Huh? Okay? So this is a movement along the land curve. Now the other thing that you can do is rotate. What is it? V times n. Huh? So if n changes, that means your inelasticity changes, or your elasticity changes. That just means that you're going along a different slope, right? Huh? So you see what happens if you're at this level of demand and you change your price elasticity. There is a force that you have to do, right? And they call that a rotation of the demand curve for obvious reasons because it looks like a rotation. We would say, okay, the mass is increasing, right? Because we don't use this curve. We don't plot it in this curve. All right? We plot everything with vectors, you know, like this. Or, you know, and they said, yes, I'm matching kind of this picture with this picture. Okay? So here I kind of did over time, you know, you're adding. So if a dt, if I put a dt here, then you see over time I just added a little bit of mass, and that's what I pictured here. So, I guess the exercise is to see how these pictures and these pictures overlap. They're saying the same thing, you know. It's not so obvious until it's obvious. Now, economists will also talk about shifts in the demand curve. Okay. And see, we don't really do that. I mean, run this is basically what we look at, right? But not always. Well, sometimes what you do is your reference frame is not inertial, it's actually moving, right? This happens a lot. So you get pseudo forces. All right, Scheinkraft. So what happens if this thing is not going at constant speed but has a non-zero acceleration, right? Then it's going to look as if this thing is acted on by a force, because why is it moving away all of a sudden? All right? You can calculate what it is. It's got a minus sign because it's a reaction force, and it also goes with the proportional to the mass, right? Also to the price of elasticity. Okay? And that is what happens when you do a shift in the demand curve. Okay? That will move this thing to another location. All right? So this force seems to go out of nowhere and jerk it out of the origin. So you're shifting that curve. They do this all the time, shifting of the demand curve, right? And basically they say market demand will change, therefore you will blah, 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 right? Okay? From our perspective, it's just a pseudo force, because our reference frame is a moving reference frame. So this is called, I believe, the D'Alembert force, where if you're pushed back in your chair, if you're the car that you use as a reference frame starts moving, right? Okay. So they call that a shift.
It also shift downwards.
Yeah, sure. You just shift backwards. You just accelerate down. You see? Down and up is the same as left and right because it's a whole line, right? Yeah, I like your remark because it's like they're so close every time, and then every time no cigar. But the reason it doesn't work is because all the work we did is setting it up, to be sure these things go to zero, to be sure we have this relativity, right? Without it, all of this is just a nice idea, but it ends up not working out. So you see the importance of all these definitions, correctly setting up, defining everything, defining momentum as a vector, economists don't do vector calculus, okay? So we actually achieved a lot here. So we have the inertial force, we have this other force, and we have these pseudo forces, all of a sudden, boom, 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 boom. All right? Things are going well for us. And you can now match up these kind of figures with these kind of figures, right? Of course, most of your thinking will occur in this, or in electrodynamics, right? So you have a coil, and then this V will be going through, and then you can change it to the flux linkage also by putting in a magnet and stuff, adding some windings. I don't know what they do. Maybe you can change this self-inductance, variable inductor.
Is it minus 10 meters?
Well, because it's a pseudo force, they tend to work in the wrong direction. All pseudo forces, they work against you, right? So,
It's not describing the line. It's describing the. If it will be the line, then the line would go downwards.
Well, you see, when this line shifts out, you can think of it as a force, but the shift is leftward, you get a positive force. Okay? You see that? Look here, the acceleration is positive and it gives a positive force. Here the acceleration is negative and gives a positive force. So you need a minus sign. That's the way to see it graphically. The way to see it is that you get pushed back in your chair when it's so when you accelerate forward, the reference frame accelerates forward, you feel a force in the other direction. Okay, and that's the minus sign. Every time you see a force on the minus side and this mass, you know it's a pseudo force. Okay, the centrifugal force, the D'Alembert force, Coriolis force, all of them are proportional to the mass with a minus sign. All right, all of them move away. Okay, that's because you take It's the reference frame itself that is doing the moving instead of you. All right? Huh? That's just a property of pseudo forces. Okay? Okay? Yeah, I mean, so you see here, like, these slides on the walls are not so big, but basically because we went through all this effort, the definitions and everything, and then kind of rolls out. It's a subtle business. And had we done any mistake there, all of this would have made no sense. Very delicate structure. Very delicate, very beautiful. Very beautiful. Very intellectually stimulating. Huh? And it's highly underappreciated because when you learn this, you go like, oh God, we just plug it in, get the right answer, go home, and get a drink. So we're cool with this, huh? So we have some time for the third law, huh? This one is actually the hardest, I feel. That one is really hard. And a lot of people get it wrong, Yeah, maybe I should say something about that, right? So you guys know what action or the reaction is, right? Huh? So if I have this here, what's the action force? Say this is the action force, this thing going down. Huh? All right. Huh? What's the reaction force? You know? No. Oh, no. No, that's just a motive force. That's just the action and reaction force has to be always there. Right? Action comes with reaction. What if I take the hand away? What happened to the reaction force? So it can't be the hand.
Correct. Whatever.
Yeah, but what is the reaction force then? If this thing is just let go, it's more moving, but there's still action is still equal to reaction. What?
Gravity around position.
Yeah, so gravity, right? So that's the action force, right? And what's the reaction force?
You're gonna follow gravity from that thing to the.
I know what you're saying, but think now of this. Here's an object and here's another object. And this object is pulling all that in this thing. Huh?
Yeah, the mirror also pulling, or the object is also pulling.
That's right. That's right. So this force is just a force that happens to be there. It's just a motive force, but it's not the reaction force. You see? So you add it, of course, to your answer, and it was a trick question. Okay? But action is always equal to reaction. You see, this is always the case. You put something underneath that. It's not always going to get away. All right? Huh? So this is just to prove to you that this is slightly more involved than you thought it was. All right? Huh? Okay.
With your hand on it, there's another set of forces that adds up onto this.
Yeah, there's another set with its own action and its own reaction, sure. Right? Huh? You can do that, right? So there's Diane, and then there's a reaction force. I don't know. Huh? No. Is it your feet or something? I don't know what that is. Huh? Okay. Huh? And then you just have these motive forces that are just acting with each other. Right? Okay. Huh? But all forces come in pairs, right? Action and reaction. Okay. Huh? And it's always, you see, the interaction between two bodies, right? It has to be two massive bodies. See, Newton was thinking of gravity, so he had to do this, right? He doesn't have hands and springs, he's thinking of gravity. So he has to realize that these things are always balance. Now, of course, this Earth is so huge and this thing is small, you won't notice it. But if it's the moon and the Earth, you'll definitely notice something. Okay? Huh? All right? Huh? Okay. All right. Now, if things come in pairs, that means so action and reaction is a description of an interaction of two objects. Right? So you need at least two objects in this world to have action equal reaction. Okay? Huh? So, if an object is an agent, what is the first law, the third law mean then? That you need at least two agents, okay, that are interacting. Okay? Huh? Okay? So, what does that mean? Well, you have two, that this idea of price being value has to be something that occurs in pairs of agents. So a party and a counterparty, right? So this notion of value that is analogous to Newton's notion of momentum has to be something that Smith calls the value in exchange, you know? So it's not value. You see, you have all kinds of values. You have also value in use. What it's worth to me, independent, right? I just love this and I don't care what everybody else, okay? It's true. Like a net present value is also just you. You just assign to this cash flow as value, bye-bye, right? Okay, and there's nothing to do with exchange and nothing to do with trade. There's just you, right? But that's not the kind of price or value that Newton is talking about, because the only thing he's talking about is something that is defined in an exchange between two people, okay? That's exactly what the law of demand is trying to do, because demand and supply, there are two sides to the same coin, okay? So I have a quote here from Adam Smith, where he tries to make this point, okay? So he was the first to see that value in exchange and value in use, as he called them, were two different things. So he says, well, why is it? See, that if, first of all, he said, we all know that water is way more valuable than diamonds, right? Sure. Okay, these diamonds. He says, why is it that water is so cheap and diamonds are so expensive? Okay? That's because cheap and expensive do not refer to some kind of value that you happen to assign, but it's a value that he called the value in exchange. Okay? Huh? So value, when you're exchanging this with somebody else, then you value this in that context at a certain level. All right? That level is that price level. Okay, that we're talking about. That's the price we're talking about. Okay? Huh? So this is a very important point, because if you don't make this point, the third law won't hold, and if the third law won't hold, you won't have conservation of momentum, and therefore there will be no conservation of price. Okay? The price will make no sense. You can't write down Newton's law. All right? Huh? Okay? So to see that our P is what we call price, you got to be very specific about exactly what this is. Okay? Huh? Now, again, dependent on which analog we use, the mobility or the impedance analogy, all right, you can see this in different ways. So in the mobility analog, a force or one, that's a flow of value, right? Okay, we use this FSP dot idea, a value flux, you could call it, right? And all it's saying is that it's a conservative flow, so that the amount of price of value flowing from is conserved in this interaction, the total amount of value. So this person decreases in value, that person should increase in value. All right? This is not just value coming out of nowhere, this is value in exchange, right? Huh? Couldn't be that I just rethought things and I'm more happy now. Huh? Okay? Okay, that's one way to look at it. So that's very akin to our way of thinking of conservation of momentum, right? So conservation of price is a little bit awkward, right? You know, what you could do is say, well, instead of the total price, so we have millions of these agents, I look at, and instead of the total price, I look at the average price. It's the same as the total, right? Which is divided by some number. And what I'll say is that this average will remain constant in the interaction. So the average price level within a system or an economy will remain constant. And that's the picture of conservation of momentum. Okay? But this will not hold if you have a wrong idea of what price is, if you don't have the third law. Okay, so the price level within a closed system would then change. Okay, and this one it doesn't. Okay, so the law of conservation of momentum, I like to think of it as the law of conservation of value in exchange, or the law of conservation of the average price level. All right. Now, there is one more way to look at it, and that's more from the marginalist kind of theory of demand, right? So what does an economist do? So they have here the supply line, here's the demand line, right? Goes the wrong way. Well, that's convenient, since I have this minus sign here anyway. I'm going to do it this way, right? Yeah? All right. So I will just see how, if the price goes down, it's a negative one for this guy and a positive one for that one. But you see from the way they draw it, they precisely cancel out. All right, otherwise this wouldn't work. You see? So this is saying precisely what this is. All right, so by drawing these demand and supply lines in this way and flipping this one, you can show that action and reaction has to be always the same. All right, here. So built into this picture is Newton's third law. All right. Okay. Now we call this action and reaction. It means, of course, the force of action and the force of reaction. The force is a momentum change action, you know. So momentum goes in by gravity and then goes out, but you know the other way. All right. So it's nice to think of it as price action equals price reaction. I mean, a lot of, especially in finance, we talk about the price action of something. So it's going up, then it always has to be a price reaction of some other type, right? Now this normally is all positive, but don't forget the minus sign here because this guy's going down and this guy's going up. All right, and there you get the right flip again. All right. Okay.
It's like the demand and supply only hold in an equilibrium position, because otherwise there could be like more demand than supply.
Yeah, this is just shorthand for something that always holds no matter what, right? So these things will be moving, right? And still these forces are equal. Okay? You see?
I can see it in the left picture, but I don't really see it there.
Oh, you don't see it here?
There could be a situation where
No, because this one is not in equilibrium is here. And they're not in equilibrium. So we're done. In equilibrium will work too, so.
like in a real life situation when there's more demand than supply.
You see, of course, you can have a situation where there's more demand of supply because you're pushing at it or the thing is going somewhere else, and you'll have another action reaction pair, right? You see, so in real life it gets complicated why you get movement. Okay, that's the same in Newtonian mechanics. You can't assume that action and reaction only is true in equilibrium. Now it's always true. The forces always come in pairs, except the way these pairs work is going to be, you know. So if I shoot a gun, of course the bullet will come out, but I'll still get the recoil. Somehow I have to absorb the recoil, right? Or if I push this forward, I have to somehow push myself back. Right? That doesn't mean I can't get this table to move if I, you know, you just have to realize that if you have a good example is a rocket, right? So the Apollo, whatever, that went to the moon. There was an article in the New York Times, you know, that's not a very good newspaper, but even in those days, they argued that you could never get to the moon because there was nothing to push yourself against. Okay, it's not like a propeller airplane or you're running. It's clearly you're pushing yourself against. And on space they said there's nothing, therefore it's possible. Okay, and they didn't see that it's true. If you can't push yourself against something, then you're not going to move, right? So in order to get an action force, you've got to have some idea of where that reaction is going to go, right? So you got to hold your gun before you shoot it, otherwise the gun will just fly off, right? Okay. So, but what they didn't see was that the rocket pushes itself against its own exhaust fuels, and it just drops those, and then in the end it comes back like this, and it was like that, right? So these guys have thought of it, and they've done it this way. Right? So you see the necessity of getting movement or providing for something that can absorb the recoil, the reaction force. Okay, and that's the sign here. So don't think it's always in equilibrium with something. That was my example, like what's the reaction force? Well, it's not the hand, Now it's not in equilibrium, but action and reaction are the same. All right? It's a good question. All right? Because it's very confusing, this stuff. But it's nevertheless, true. You see? Is that clear? Did I make it clear? So they just come in pairs. That's what Newton said. So if you have a whole system, this is what makes these central math things work. You have all this stuff, all these agents, and all of them are trading. Then this one comes in that pair, that one comes in that pair, right? So if you look at the whole thing, it all adds up to nothing. Right? So it's not going to do anything, right, to the whole system, right? So you can push this whole system, and then it will act as if the center of mass is moving, right? And this whole thing, it may be expanding or contracting, but the thing is not going to move fast because it can't pull itself up by its own shoelaces. So that's what it's saying, right? So you have this picture of the Baron von Munchausen, if you know this. And he did all these incredible things. And one of the things he did was pull himself up by his own shoelaces, right? So the reason that doesn't work, I mean, I see you smiling, but the reason it doesn't work is you don't have any reaction force. You haven't provided for a reaction force. It's not going to work, Or he pulled himself up out of a morass by the hair of his horse or something crazy, So you can't sit on a sailboat and blow in the winds, because there's no reaction force. You have to be separate from the boat. That's the sign here. So in order to bring up your price, somebody else has to lower it, but lower it means bring it up on the other side of the transaction. Okay? So you both have to change that amount of value. That's what all this is saying. All right? Okay, so that brings us to the last law. And so I hope I've given you guys two things. First of all, Newton's system is non-trivial, right? Which is something that you might think when you just study Newtonian mechanics. And the other thing is that it's actually a lot of work, but it works to place economics in that thing. But what you've got to see is that your notions of price and your notions of demand, they're very, very precise, okay? And you can't deviate from that in your modeling, all right? Okay? And you're a little bit in the same situation where people were when they first started applying Newton's mechanics, and their idea of a force and Newton's idea were not the same, right? So they're saying, well, this thing is slowing down. They said, well, there must be another force, and it's called friction, and then they started doing this, right? Okay? There's a famous episode in Newtonian Mechanics where Newton, he predicts that these things go in these ellipses, and instead of circles, and he gets it right. And then somebody knew that one of them does something like this. I think it did something like that. Okay. So, well, the conclusion they had is, well, this is a little bit weird. It makes an unnatural motion, whatever this is, right? And then, so he says, well, Newton's law must be wrong because how you can't get this thing out of it. And then some clever guy says, well, maybe he's right. It's just that we forgot to model a force. All right. Now let me assume there's a planet here, and that's pulling at it, and when it gets in here, now it gets pulled a little bit, and then it moves away, and then that's how we get this little bubble, right? So he calculated where that planet should be, right? And then they saw that that thing is almost always hidden. You can't see it. So it's on the wrong side of the Earth. I don't know exactly how they do it. But then on a special place, on a special day, you could actually see it. So they went in and then they were like, oh, we're going to prove a rumor, but there it was. Okay. So then you're in business. And it's not just a mental exercise to say, I have a new idea of force. Now you're really predicting stuff. Then you're in business. That's what I want you to get here too. So not only are we recasting all these things in a different framework, but I want you to get that same feeling that now you're in business. So now you see some economic phenomenon. All I got to do is go search for the force that's causing it, right? I don't have to assume something new and weird, No, everything is about force. Just find it, okay? And then when I'm satisfied, okay, there's a little thing here, I don't really care. I'm not going to worry about that, right? So, okay? And that's the search. So you get it in your head. What is an economic force? What is price? How do I do this? Then you start observing and say, well, if it's not doing what my model is doing, then that means there must be something else. Let's go look for it. Let's go look for that. Okay? It could be so complicated that you'll never find enough stuff to get close. But that's not our business, Then you look for another problem where it's relatively simple, but another person couldn't do it. Okay? That's the spirit you got to do this. So that's why you have to really get a good feel for these definitions, because in mechanics, so many problems have been solved for you, and then you just find the right way, and then you work your way through, But here, that's not the case, and you got to have a little deeper understanding of what these principles are. The students who've been here a while, they can tell you that. If you don't do that, your research comes to a screeching halt. You become extremely frustrated, etc. Okay. All right. With that, I went a little bit over time, but let's end the